is not necessarily dilatation analytic. This means that the effect of the symmetry breaking tends to amplify over successive SCF iterations. And as we will see from some equation later on, this problem is very severe when the homolume band gap is small. And thus the solution we advocate is that high-level many-body treatments of electron correlation have to restore symmetry breaking. The problem is that once the symmetry of the wave function is broken, one has to work harder to compensate the unphysical starting point. Because this means in practice that the convergence towards the full CI limit is slower. And thus therefore, we always strongly advocate restricted wave functions as zero-order solutions in post-SCF calculations. Thus the symmetry breaking is really an artifact, as you can see here in the case of benzene. Thus we compare energies obtained at the restricted Hartree fork and unrestricted Hartree fork level. Thus using improving treatment in correlation. Thus you see that at the Hartree fork level, the most stable solution is the spin unrestricted one, the singlet open shell species. But as soon as you include correlation, then the energy order reverses in favor of the restricted solution, the singlet closed shell solution. The same here if you do calculations with bigger basis set and this correlation treatment, and P2 and P3 and P4, because at the Hartree fork level, thus we have the unrestricted solution as the most stable solution, but as soon as we include dynamic correlation, then we get the restricted solution back. So there are different diagnostics that have been developed in order to evaluate the extent of multi-reference character and thus of the singlet open shell character of molecules. One is the so-called T1 diagnostics of couple cluster theory. Well, this diagnostic has been quite strongly criticized in the literature. Thus we also rely on another diagnostic that was devised by Jan Martin and his co-workers in this paper here. And this is based on the calculation of the percentage of the total atomization energy, which is accounted for by parenthetical connected triple excitations in CCSDT calculation. And if this quantity is smaller than 2%, this indicates that we have a system that is strongly dominated by dynamical correlation. Because as you can see from this table, well, this is the case until octacene. And then beyond that, then the threshold is passed, and then this may indicate that for systems like monacene, decacene, and decacene, multi-reference effect may indeed start to be important. Just to summarize this section on the electronic ground state of acenes, thus we've seen that high electron correlation treatments and large basis sets are required for predicting the correct spin multiplicity and the symmetry of the electronic ground state. Also, despite an increasing character, the electronic ground state retains a singlet spin multiplicity up to an decacene and probably much beyond. Thus, extrapolation of energy indicates a vanishing singlet triplet energy gap when we go to the limit of an infinitely large system, and this within an accuracy of 0.06 electron volt. Because I didn't have time to show results, thus you can find the results corresponding to systems larger than heptacene in this paper here. Also, we have seen that the singlet open shell or anti-ferromagnetic nature of the electronic ground state of acenes in spin unrestricted DFT calculations is artifactual, and this is necessarily the result of a too approximate treatment of electron correlation. Thus, having noticed that, then we realized that in the literature there was a main issue regarding the half metallicity of zigzag graphene nanoribbon, which basically exploits the idea of a symmetry breaking in between spin alpha and spin beta densities. Thus, it was also quite clear to us that this should be re-examined, and this is why we have this second section in my talk. Because I will show you now that the half metallicity of graphene nanoflakes is more a hype for material scientists than a real new quantum mechanical Eldorado for nanotechnologies. What is half metallicity? Well, half metallicity implies in graphene nanoribbons the coexistence of metallic nature for electrons of one spin orientation and insulating nature for electrons of the opposite spin orientation. And half metallicity has been predicted for zigzag graphene nanoribbons from so-called first principle calculations employing spin unrestricted density functional theory. This was published in a very famous paper by Louis Cohen and Son in Nature in 2006. And if you look at citation index, this paper is probably being cited more than 1,000 times so far. The problem is that half metallicity finds its origin into symmetry breakings in spin densities, and as you have seen, these are artifacts due to two approximate treatment of electron correlation. So suppose you have a zigzag graphene nanoribbon, which is was drawn here, and you apply a perpendicular external field. What you observe according to unrestricted DFT calculation is the following. This is what we get as zero field. Thus we have a symmetry breaking in spin densities. There's localization of spin alpha on one side and of spin beta on the other side of the zigzag graphene nanoribbon. And this because they are localized in different regions of space, when you apply an external field, well, they experience different effect. Electrons belonging to the spin alpha system are stabilized. Electrons belonging to the beta spin system are destabilized. In the spin alpha system, we observe an opening of the band gap. In the spin beta system, on the contrary, we observe a closing of the band gap. Those electrons of spin alpha would become insulating, while electrons of spin beta would become metallic. That's why we have so-called half metallicity. And thus this paper in Nature has initiated great excitement among theoreticians and experimentalists, because it appears that this was the right material for the making of spintronic device. There's a new technology in which the information is not carried by the electron charge, but by the electron spin. That's why this finding has made so much excitement in the scientific literature. So this finding is based on the theorem by Professor Lee from Princeton University, which say that the spin of a ground state, according to a Vue-Power model in a bipartite lattice, satisfies this relationship here. There's 2s is equal to Na minus Nb, with Na and B the number of different sides in bipartite lattice. And thus in the case of a compensated bipartite lattice, like a graphene nanoribbon, we have an equal number of sides in the two sublattice, Na is equal to Nb. Thus the total spin must be 0. Thus we have a singlet state, and thus according to the symmetry broken wave function, we have an antiferromagnetic singlet ground state. So let's remind the situation so far. The spin unrestricted one determinantal artifact of DFT calculations on zigzag graphene nanoribbons lead to symmetry breaking of spin densities in so-called singlet open shell antiferromagnetic eigenstates, because we have total spin 0. And the reason is that we have different localization of orbitals with opposite spin on the two sides of the graphene nanoribbon, and this is due to a two approximate treatment of electronic correlation. And as I will show, the result is that we violate very well-established principles and basic theorems of non-relativistic quantum mechanics, like point group theory and spin quantization. Thus, indeed, canonical orbiters have to transform according to irreducible representations of the symmetry point group, which is dictated by the full Hamiltonian, and thus by the nuclear configuration within the frame of the Born-Oppenheimer approximation. And also, eigenfunctions of spin-free Hamiltonians have to be pure spin states. They have to be singlet, they have to be doublet, they have to be triplet, etc. So to analyze this in more detail, I will proceed as follows. In the first part, we will analytically investigate the scaling properties of the spin contamination in zigzag graphene nanoribbons by means of the formulae of crystalline orbiters for extended systems with periodicity in one dimension. Then to proceed further and to crash down this idea, I will show you that if we do things in a very careless way, because if we take the most approximate wave function, unrestricted Hartree-Fock S23G, thus we can show that even naphthalene can be described as the smallest half-metallic and antiferromagnetic zigzag graphene nano-island, which is of course completely absurd. We do that because people as famous as Gustavo Scuderia and his co-workers have published a paper in Physical Review Letters describing that the larger polycyclic aromatic hydrocarbon named anthracene is actually the smallest asymptotic and antiferromagnetic zigzag graphene nano-island according to some unrestricted DFT calculations they did. And then at last, we will verify computationally the scaling properties of the spin contamination and its relationship with the metallicity of zigzag graphene nano-islands and nano-ribbons. Thus, it is known from the literature that for any single determinantal spin unrestricted wave function, the expectation value of the S square operator is of this form. Thus, Sz is the Z component of the spin momentum, and B is the number of electrons of spin beta, and then we have to make this summation here over the square of the overlap between spin alpha and spin beta molecular orbitals. And then, as always, we expand these molecular orbitals as linear combinations of k atomic functions under the constraints of orthogonality for spin functions that relate to the same spin. And thus here we use this notation for the overlap matrix elements, and since we have orthogonality, this must be equal to delta PQ. Thus we suppose that we have a symmetry breaking in spin densities, thus we assume that there is some difference in between the spin beta and spin alpha molecular orbital, and thus we expand them accordingly using this formula in the L0 formalism. And then in doing so, we find that the error in the expectation value of the S square operator, because the so-called spin contamination, can be decomposed into two contributions. There's one contribution which is of first order with respect to the symmetry breaking, and the second contribution, which is of second order with respect to the symmetry breaking. And as you can see from this expression here, well, this quantity is obviously negative. Well, it's easy to show that the first order contribution is positive, because well, we get this relationship here, and obviously the real part of this overlap here is smaller than 1. Because altogether, delta 1 must be smaller or equal to 0. Thus we know that if the electron ground state is a singlet, the spin contamination can only arise through admixtures of states with higher spin multiplicity, the triplets, quintet, etc. And thus the spin contamination can only be positive or equal to 0. Because this implies this equality here. Thus we now consider crystalline orbitals for systems with periodicity in one dimension, as derived in this picture here. Thus they are expanded according to this formula here. Thus in this formula, NL is the number of unit cells within the regional space that is limited under the constraints of the cyclic Born-von conditions. Thus this is what solid state physicists refer to as the number of unit cells in the supercell. A is the width of the cell, J defines the index of the cell, and then here we have the residual coefficients and the atomic functions. Thus gamma Pg here corresponds to the atomic function on atom P within cell G. Thus the same way we can define crystalline spin orbital difference between spin alpha and spin beta crystalline orbitals this way, we can expand them in terms of the crystalline orbitals using this formula here. Thus all these functions are periodic, thus they have translational symmetry, and thus they can be constructed as linear combinations of symmetry adapted functions, which are commonly referred to as block functions, given in this formula here. And thus since they are translation symmetry adapted, crystalline orbitals with different electron momentum k, thus cannot combine, they cannot overlap the orbitals. We have block diagonalization in k. Also, we will turn to the macroscopic limit, thus given thus an infinite system with finite densities, and we will make use of this equivalence here. Thus we will turn this summation over cells into integration over the first Brillouin zone. Let's proceed now with the first order contribution to spin contamination. Thus we translate it in terms of crystalline orbiters. We carry lattice sum summations, and thus after some mathematics, we get this quite complicated formula here. Thus we see that we have a double summation over cell indices here. The key point is that we have these overlap matrix elements here that decay exponentially with respect to the distance between cells, thus with respect to the difference J prime minus J. And thus we can use translation symmetry to simplify this formula. Thus doing so, we can write that SPQ GG prime is equal to SPQ null G second, with G second the difference in between G prime and minus J. And then we can also turn this double summation over cell indices into n null times a single summation over cell indices G second. Thus doing so, and upon exploiting translation symmetry, thus we can reduce the first order term to this expression here, where gamma nk is given by this formula here. And the key point is that this summation over G second must be necessarily bounded because all coefficients here, SPQ null G second, decay exponentially with J second. Thus, if we do that, in the macroscopic limit, we find that the first order contribution to spin contamination is necessarily proportional to the number of unit cells in the supercell. It's the same for the second order contribution, but that's a little more complicated. Thus, we first expand it this way. We have block diagonalization in K. Then we expand it in terms of lattice summations. Thus, here we have a quadruple summation over cell indices. Again, we can use translation symmetry and periodicity of the lattice to simplify this formula. We can also transform these double summations over cell indices into n null times a single summation. And thus, if we do that, we get this formula here. Thus, playing with indices, we get this formula here. Thus, we have a double summation on G prime and G second. And again, these coefficients will decay exponentially with the cell index G prime and G second. And thus, this quantity here will be necessarily bounded in the macroscopic limit. Thus, again, we can write the second order contribution this way. Well, we introduce this quantity here and correspondingly its complex conjugate. And thus we can find that in the macroscopic limit, the second order contribution is proportional to the number of unit cells in the supercell. Thus, combining all results together, thus we find that the spin contamination does scale proportionally to the number of unit cells in the limit of an infinite system. Just to summarize what we found is in symmetry breaking situations, the spin contamination of any unrestricted single determinant electron state of acenes and extended zigzag graphene nanoribbons of finite width and periodicity in one dimension, this has to scale proportionally to system size and thus to diverge to infinity in the macroscopic limit. Thus, in other words, if we have a symmetry breaking in spin densities, in the macroscopic limit, we completely lose control upon spin. Thus, how can one then draw any conclusion about spin-related properties? That makes no sense. Well, here I will take the example of naphthalene, just to show that if we do things in a really crazy way, then any system basically can be turned into a half-metallic graphene nylon island. Because naphthalene is well known to have a D2H symmetrical group. And if you do calculations at the UHF level with the STO3G basis set, you find that you have deviations of canonical spin orbiters from this symmetrical group. But if you compare these plots, you will find that they are very comparable with concham orbiters for the H-tails of extended zigzag graphene nanoribbons, as was published by Son et al. In Nature. It's exactly the same kind of plots, or enlarged with finite polycyclic aromatic hydrocarbons, as was the case by Hot, Stuzeria in a physical review B paper in 2008. So basically, this is exactly the same thing. The question is, nobody would believe that that naphthalene is half metallic. Thus, why should we believe from DFT calculations that zigzag graphene nanoislands and zigzag graphene nanoribbons would also be half metallic? That makes no sense. So if we apply an external electric field perpendicular to the edge states of naphthalene, well, we find a half metallic split of pi orbiters. There is almost no effect on the sigma orbiters. Well, the effect of the half metallic split will decrease slightly if we increase the basis set, but we have found that even in the limit of a complete basis set, there would still be a half metallic split in this case. But again, this is what we get at the Hartree-Fock level at different value of the electric field. But we see that at the Hartree-Fock level, the unrestricted solution is the most stable one. But as soon as we include dynamic correlation by higher order treatment, NP2, NP3, etc., we find that the energy order reversed in favor of the restricted wave function at the NP2 and higher levels, thus upon inclusion of dynamic correlation. Thus, in other words, dynamic correlation quench anti-ferromagnetism and half metallicity in naphthalene. So on this slide, I show results obtained for a scene of increasing size at this level, unrestricted Hartree-Fock with a 631G star-star basis set. And you see that the extent of the half metallic split increase with increasing system size. And this can be understood from the equations which governs the conversions of wave expansion coefficients of wave functions in symmetry breaking situations. So this equation was derived by Söderholm and his co-workers in the 70s by means of one-electron perturbation theory. And here, Q is the order in the perturbation expansion, while D here, the first order term, corresponds to minus the energy gradient in the direction of the symmetry breaking transformation. Since the Fock operator is Hamiltonian in an SCF calculation, it can be shown that these orbital energy differences here must necessarily relate to differences between unoccupied and occupied orbiters. And thus you can see that when we have near energy degeneracy situations, that's when the Von Band gap is becoming small, then the convergence of the LCR coefficients is going to become more and more problematic. And does this explain why the extent of the half metallic split increase with increasing system size? It's the same if we consider larger graphene nanoribbons, so-called 4 times N. Thus this compound here is antantrene. Thus this is the compound that was described by Scuderia as the smallest nanographene nanoisland which can be half metallic. And here also you see that the extent of the half metallic split increase with increasing system size. On this slide, I display the evolution of the HOMO-LUMO band gap as a function of the number of unit cells. And quite strangely, we find that in the A-scene series, well, the band gap first decreases before increasing again. And this abnormal behavior actually is the consequence of the symmetry breaking of the electric wave function at the UHF level, and this prevents the closure of the band gap. Thus, we also computed what we call the half metallicity index by taking the difference of energy derivative of orbiters with respect to the external electric field. And we found that for the two series we consider, A-scenes and 4 times N nanoribbons, we found that the expectation value of the S square operator, with the spin contamination, increased proportionally to N. Also, if you compare these two series here, we find that there is a factor 3, more or less, and this corresponds basically to the ratio of the size of the ratio of the width of the 4 times N versus the 2 times N series. Thus, simply this half metallicity index is basically a measure of the spin contamination, which is a methodological artifact. So on this slide, I show results which we published in a minor journal here, the Journal of Molecular Modeling in 13 was obtained using different level, Hartree fork and different functionals. Thus at the Hartree fork level, well, we see that we have from the onset, from benzene, a symmetry breaking and a perfect scaling of the spin contamination with respect to system size. And also we see that for other functionals, thus whatever the employed exchange correlation functional, the spin contamination increase linearly with the number of unit cells when we go to the limit of a very large system. Because of course, if we go to an infinite limit, we have an infinitely large spin contamination, and this is obviously in sharp contradiction with what we expect for compensated bipartite lattice. Because I remind you that according to Leaf's theorem, the total spin must be equal to 0. Because if the total spin is equal to 0, then obviously the expectation value of the S square operator should also be 0. Because there is something completely contradictory here. This conclusion, in the absence of an external spin-dependent potential, a spin-polarized or antiferromagnetic and half-metallic singlet electronic ground state in extended A-scenes and zigzag graphene nanoribbons is a mathematical impossibility. Thus, could we still have half-metallicity if we consider other factors like external perturbation, for instance, thermal fluctuations, or magnetic perturbations due to the presence of C13 nuclei in matter? Well, I don't think so, because if we consider the single-triplet energy gap of all these systems, in general, they are much larger than the thermal fluctuations, which are equal to 0.6 kilocalorie per mole at room temperature, or to magnetic perturbations due to carbon-13 nuclei in matter, which are estimated to be of the order of a few megahertz at most. Thus, in normal conditions, spontaneous spin flip rule out. Well, here in red, I provide the research we obtained for antantrene, the compound that was described by Scuderia and his co-workers as the smallest graphene nano-islands. Thus, we find a vertical single-triplet energy gap equal to 17 kilocal per mole, thus by means of our focal point analysis, of 25 kilocal per mole, sorry, and obviously this is much larger than this quantity. Thus, to conclude the whole talk, thus we have seen that single reference treatments converging to the CCSDT level in conjunction with an asymptotically complete basis set enable highly accurate insight into the electronic properties of A-scenes. Thus, this comprise ionization energies, electron attachment energies, excitation energies, and also electric polarizabilities. This was true up to hexacene and probably beyond. Thus, for all these systems, we could obtain chemical accuracy, which means 1 kilocalorie per mole or 0.04 electron volt. Also, it has been made clear that within the framework of non-relativistic quantum mechanics, an exact treatment of electron correlation must restore symmetry breaking of spin densities in single determinantal treatment, and this will necessarily quench, therefore, any antiferromagnetic and half-metallic spin polarization of H states in A-scene, graphene nanoislands and nanoribbons, and all kind of related systems. Well, we have to keep the door open, nevertheless, because physical symmetry breaking in spin densities may still be induced by spin-dependent perturbations, with think-about spin-orbit coupling interactions. Well, these are very small quantities, however, of the order of a few micro-electron volt. Thus, it is still not clear whether, if we go to the limit of an infinitely large zigzag graphene nanoribbon, whether these spin-orbit coupling interactions will be strong enough to induce some physically acceptable symmetry breaking in spin densities. Thus, the next challenge for theoreticians, therefore, would be to make possible a balanced treatment of many-body effects, electron correlation, and of spin-orbit interactions, and in this purpose, we would need many-body relativistic quantum mechanics. Yes, at this stage, I have to thank many contributors to this work. As I told at the beginning, this is a quite long story. We started in 2001. First with Dr. Alexander Trofimov from Irkutsk University in Russia and Professor Zederbaum from Heidelberg University in Germany. Then there were many people from my group involved in all these studies I have shown, PhD students like Luc Klaas, Eugene Kiashko, Professor Jean-Pierre François, Dr. Balázs Asgató, which has certainly been